Good morning, ma. In yesterday's class, we have seen what about crystal field splitting. The crystal field splitting in presence of octahedral complex, as well as crystal field splitting in presence of tetrahedral complexes we have seen. Okay, and some more points related to this crystal field splitting today we will go through. First point. Crystal field theory, CFT, it considered ligands as point charges. Crystal field theory, main assumption is okay, it considered ligands as point charges. Now, this is the central metal atom. Ligands are approaching. These are like point charges. Point charges means some charged particles. Okay, when they come near to the metal atom, ligands when they come near to the metal atom or ion has positive charge. Generally, metal positive charge only, it is involved in coordinate-covalent bond in complexes, correct? This one has positive charge. Ligands contain negative charge or lone pair of electrons. Ligands contain negative charge or lone pair of electrons. Both are considered as point charges only. When these point charges are approaching towards the central metal atom, d orbitals present in central metal atom will be varied with two sets. Means they will be differentiated into two sets depending on repulsions caused by ligands and metal. Depending on repulsions caused by ligands, as ligands are treated as point charges, that separation of d orbitals will be happening. That is the main point coming under crystal field theory. Okay. At the same time, this is remained as drawback also. In drawbacks of crystal field theory, we will see. Okay, ma'am. First, we will continue with what are the concepts we completed yesterday. Okay. Now, what is the main point considered in CFT, ma'am? Ligands, CFT considered ligands as point charges. Okay. Even the ligand is negative charge or some lone pair of electrons ligand. Okay. It is considered as some point charge. When it approaches to the central metal atom, there will be a repulsion between that ligand and metal. Because of that, d orbitals present in that metal atom will face some repulsions, and there is happened with crystal field splitting. That is the thing. When those ligands are approaching along the axis, the orbitals which are present lobes with along the axis, their energies will be increased. When that ligands approach in between the axis, so the orbitals which contain lobes in between the axis, orbitals energy level will be increased. That is happened in octahedral and tetrahedral complexes respectively. Okay, ma'am. Now, in your textbook, under the heading spectrochemical series, in your textbook under the heading spectrochemical series, they gave the order of strength of ligands. Example, F minus is less than, Cl minus is less than, like that, etc. Less than, water less than, NH3 less than, Cl minus, like that. Some order is given in your textbook. Correctly, I did not remember, ma'am, but you can practice 2 or more 3 odd times. Definitely you can remember, no problem at all. Okay, this is the spectrochemical series. In that spectrochemical series, note down one point, that is from left to up to water. From left to up to water, these are all weak field ligands. This all the halogens are kept under weak field ligands only. Just observe the weak spectrochemical series. Okay, in that spectrochemical series, all the ligands F minus, Cl minus, I minus, all are kept under weak field ligands only. Including water also, it is included as weak field ligand. So tick that one. Up to water, weak field ligands. From next to water onwards up to last, those are strong field ligands. What is that now? In petrochemical series, they give the order of ligands, strength of ligands. Okay, that arrangement of strength of ligands in the increasing order of strengths is called petrochemical series. In that up to water, including water also, that those are all weak field ligands. Next to water, next to ligand onwards up to last. Okay, those are strong field ligands. Yesterday what did I write? In presence of weak field ligands, delta naught is less than P. In presence of strong field ligands, delta naught is greater than P. Then what will be happen? In today's class we will see. Okay, ma? So what is the assumption, main assumption CFT made? That one previous point I took. They treated as ligands as point charges. And next, this classification was given by successfully CFT. That is strong field ligands and weak field ligands. Okay, ma, everyone? And one more point. In octahedral complex, we wrote the splitting of d orbitals as 2 orbitals above and 3 orbitals below. Na? Okay, this is the T2G set, this is EG set, and the center line, this is called Barry center, BARY, BARY, Barry center, that is called Barry center, and this one is 3/5 of delta naught, and this is 2/5 of delta naught, and total this is delta naught. What is the meaning of this one? Out of total delta naught, this splitting from Barry center, no? This is Barry center. Okay, Barry center means all the 5 orbitals have same energy. From that Barry center, out of 5 parts, 3 parts raised by 2 orbitals. Okay, 2 parts getting down by 3 orbitals. That is the meaning. So this is 3/5 of delta naught. This is 2/5 of delta naught. Just no need to confuse. Just remember, here 2 orbitals are there, then 3/5. Here 3 orbitals are there, then 2/5. This is in octahedral complex. Next, in tetrahedral complex, before that, all the 5 d orbitals here, everything is same. Just to represent this one only I give. In yesterday's diagram itself, you can write this one, no problem. Again, no need to draw. In yesterday, we have written in octahedral complex, in tetrahedral complex, splitting of crystal peak splitting, we have written. In that itself, you can write this one. Okay. Coming to this tetrahedral complex, ligands will approach in between the axis. So 3 d orbitals are above and 2 d orbitals are below. This is T2G set, this is EG set, and coming to this is Barry center, BARY, Barry center, and this is 2/5 of delta T. This is tetrahedral complex, na? 2 by 5 of delta T. This is 3 by 5 of delta T. Opposite, just opposite. And the relation between delta T and delta naught is delta T is equal to 4 by 9 of delta naught. Delta T is equal to 4 by 9 of delta naught. Okay, just note down this information in yesterday's diagram itself. After completion of those two diagrams, note down this information and keep it in box. This is the relation between splitting of energies in tetrahedral complex and splitting of energies in octahedral complex. Delta T is equal to 4 by 9 of delta naught. Okay, ma'am? Okay, note down this information after completion of this. Okay, what about strong field ligand and what about weak field ligand? That one clearly we will see by taking the examples. In previous topic, that is valence bond theory, magnetic properties, we have taken examples. That examples itself we will take and we will explain here. Okay, let us see that one. In magnetic properties of coordination compounds, D1, D2, D3 configurations, no problem. Like that we have seen under valence bond theory. After that, D4. D4 onwards we have seen. Okay, let us see. D4, manganese. MnCN6 minus 3. Just 1 minute more. Manganese 4s2 3d5. Okay, minus 3. MnCN6 minus 3. Now, first, as we know now, which is strong field ligand, which is weak field ligand. Okay, now first we have to write this ligand is Cn minus. Cn minus is strong field ligand. No problem, once go through that spectrochemical series now. No problem at all. Okay, you will remember. Cn minus is strong field ligand. Coming to this, in this oxidation number of manganese is plus 3. Mn plus 3. This Mn plus 3 configuration is argon, 3d4. What is that? Argon 3d4. What is happening here? 3d4 means here manganese atomic number is argon 3d5 4s2. Okay. Mn plus 3 means 3 electrons must be removed. Then it will become 3d4 4s0. So I am writing here 4s0 4p0. Okay. We have to get clarity that why these electrons are getting paired inside in this 3d4 ma. For MnCN6, if you observe 1, 2, 3, 4th electron we wrote here, not here. Pairing is taken place inside. Like that we have seen in MnF6 minus, reverse is happened. We wrote here. Hund's rule is violated. Correct, ma? Now you will understand why it is. This is octahedral complex, na? In octahedral complex, these 5 d orbitals are there, na? 5 d orbitals. They are split into sets. For your understanding purpose, I am writing clearly like this. For every complex, no need to write like this one. Easily you will understand, no problem. Like this. Okay, now this is EG set, this is T2G set. Under the presence of strong field icon, I wrote one point, that is delta naught. This is delta naught fully. This delta naught is greater than P. Delta naught is greater than P, meaning the splitting of energy is very high. The splitting of energy is very high, which is greater than pairing energy. Okay, now you will understand. See, this is the data we have. Okay, Cn minus is strong field icon. How many electrons present in 3D? 4 electrons. Okay, now first electron 1, second electron 2, third electron 3. Fourth electron we have to think about. Okay, that fourth electron should come here. According to Hund's rule, that fourth electron should come here. But what is the problem here? The problem is that delta naught is very high. Delta naught is very high. Then what this fourth electron will do? The fourth electron, instead of entering into that much higher energy, it will enter into lower energy itself. It will undergo pairing. By pairing, energy will be released. By pairing, energy will be released. Okay, that energy is lower than delta naught. So electron will prefer pairing energy. Electron will prefer pairing energy instead of entering into fourth orbital. Once again, this is Cn minus, which is strong field icon. In presence of strong field icon, what is the condition? Delta naught is greater than P. What is the meaning of delta naught is greater than P? Means the splitting is very high, like this. When the splitting is very high, this electron will choose to pair. This electron will choose to pair instead of entering into fourth orbital. Instead of entering into fourth orbital, this electron wants to pair with already present electron by violating Hund's rule also, because this P is smaller than delta naught. This is happened in presence of strong field icon. That's why we wrote configuration of 3D4 as in MnCN6 minus 3, 1, 2, 3, 4. 2 orbitals are vacant. Then these 2 orbitals and S orbital and P orbitals, they will undergo which hybridization? D2 sp3. Which hybridization? D2 sp3. And its magnetic data, it is paramagnetic with 2 unpaired electrons. Paramagnetic with 2 unpaired electrons. This is why this electron is getting paired with this first electron. Okay, because delta naught is very high, that is called quantitative interpretation of magnetic data. That is called quantitative interpretation of magnetic data. That quantitative interpretation of magnetic data was not given by valence bond theory, which was successfully given by crystal field theory. Okay, observe the diagram, all of you. See towards the board clearly, all of you. First I took example MnCN6 minus 3. In that, what is the oxidation number of manganese? plus 3. Electronic configuration argon 3d4. Okay, that 4 electrons I wrote as 1, 2, 3, and that 4th electron is entering into first orbital by violating Hund's rule. Why? This is the reason. In this complex, Cn minus is strong field ligand. In presence of the strong field ligand, delta naught is greater than P, in which the delta naught is very high. Means splitting is very high. Because of that 4th electron, instead of entering into 4th orbital, it is entering into lower energy. That means which is preferable for electron to be paired. P means pairing energy. Okay. So when which is greater, delta naught is greater than P. So which is smaller value, electron will choose that one. So it has chosen P. Then it is paired with first electron. Same thing if you take MnCl6 minus 3. It is not like this one. Now I'm going to tell that one also. Let us see. Same like this. MnCl6 minus 3. Now Cl minus is weak field ligand. Cl minus is weak field ligand. Mn plus 3 configuration same. In presence of weak field ligand, delta naught is less than P. In presence of weak field ligand, delta naught is less than P. Then what is going to be happened? These 4 electrons are not writing now. Splitting of energies will be same only. This is also octahedral complex only. This is also octahedral complex, so 3 orbitals will be below, 2 orbitals will be above. Correct only. But the thing is, delta naught is less than P. Means splitting of energy, these 2 energy levels are nearby each other. This splitting is very small because weak field ligand cannot apply that much repulsion force. Weak field ligand cannot apply that much repulsion force. Because of that, the splitting is small only. And splitting is small, delta naught is small. Then this difference is low. In presence of weak field ligand, this difference is low. This is delta naught. When this difference is low, what will be happen? Electrons, 4 electrons are there na? 1, 2, 3. 4th electron, instead of pairing, it will enter into 4th orbital alone by following Hund's rule. Because delta naught is smaller na, it can enter into that 4th orbital easily. So we will write electronic configuration as 1, 2, 3, 4. 2 orbitals at a time they are not available. Then it will use 4d orbitals, outer orbital complex. So this is outer orbital complex. Then this is paramagnetic with how many unpaired electrons? 4 unpaired electrons. And electronic hybridization one, sp3d2. It will use outer orbitals to undergo hybridization. 4s0, 4p0, 4d. From 4d, 2 orbitals will be involved in hybridization. Correct? Then hybridization is sp3d2, paramagnetic nature with 4 unpaired electrons. This data was given by valence bond theory. But why in this MnCl6 minus 3 this pairing is not taking place, but in MnCl6 minus 3 we got the pairing. The clarification was given by CFT. See towards the board, all of you. I hope you are clear, ma. So first one, cyanide, strong field ligand. Now Cl minus, weak field ligand. Next example, third one. Same explanation will be continued. FeCN6 minus 3. FeCN6 minus 3. In this, what is the oxidation number of iron? Fe plus 3. Fe plus 3 configuration is argon 3d5. In this, cyanide is strong field ligand. Then 3d5 can be written as 1, 2, 3. Strong field ligand means delta naught is greater than Pma. Then fourth electron cannot enter into fourth orbital. It will be paired with first orbital, second orbital, fifth electron here. Then two orbitals are available, which undergoes inner orbital complex. Inner orbital complex or low spin complex. Inner orbital complex or low spin complex. This is paramagnetic nature. With one unpaired electron. This is paramagnetic in nature with one unpaired electron. Everything was successfully explained. Even why this pairing is taking place also now you are clear. 3 orbitals are below, 2 orbitals are above. That splitting is very high. Then fourth electron is entering into that first orbital only. Fifth electron is entering into second orbital, in which pairing is taking place. Delta naught is greater than P naught, so they will prefer P. Instead of entering into that higher energy orbital, they will enter into that lower energy and they are getting paired. This is about FeCN6 minus 3. Okay? Next. Same thing, FeF6 minus 3. F minus is weak field ligand. Then this configuration written as delta naught is less than P naught. In presence of weak field ligand, delta naught is less than P. Then these 5 electrons 1, 2, 3, 4, 5 paramagnetic nature with 5 unpaired electrons. Okay, next. It cannot use these 2 orbitals 3D, so it will use outer 4D orbitals and hybridization is sp3d2. Outer orbital complex. High spin complex. Everything I give clear data. I give clear data in valence bond theory itself. Now simply I am writing down. Okay, why this pairing is taking place in some complexes and why this pairing is not taking place in some complexes. The clarity I am giving now. Okay, this is about 4th example. Next, 5th example. CO C2O4 thrice minus 3. One exceptional case is C2O4 minus 2. In that order, it is before water only. It is weak field ligand only. C2O4 minus 2, it is weak field ligand only. But with cobalt only, C2O4 minus 2 with cobalt only, it is acting as strong field ligand. That reason also I will check and I will say C2O4 minus 2 with cobalt alone, it is acting as strong field ligand. Then in this complex, what is the oxygen state of cobalt? CO plus 3. CO plus 3 configuration, argon 3d6. Then this is strong field ligand. Delta naught is greater than P. These 6 electrons, what is going to be happen? 1, 2, 3, 4, 5, 6. Without entering into 4th orbital, that electron is entering into 1st. Next 5th electron is entering into 2nd. 6th electron is entering into 3rd. Why the pairing is taking place? Because delta naught is greater than P. Okay, then this one will undergo D2sp3, inner orbital complex, inner orbital, low spin, and this is diamagnetic in nature. This is the reason why these electrons are getting paired and Hund's rule is violated, because this splitting is very high. So instead of entering into that high energy orbital, pairing is taken place here itself, like this. That's why this is happening. These are entering into T2G. This is T2G set, this is EG set for octahedral complex. Okay, now final example. COF6 minus 3. Same. COF6 minus 3 means cobalt CO plus 3, F minus weak field ligand, F minus weak field ligand. In presence of weak field ligand, delta naught is less than P. Okay, CO plus 3 configuration, argon 3d6. Then we will write it as 1, 2, 3, 4, 5, 6. Hund's rule is followed because delta naught is smaller, na? So electron comes into 4th orbital, 5th electron comes into 5th orbital. After that, pairing is taken place here according to Hund's rule. Okay, as d orbitals are not, 3d orbitals are not available, it will undergo sp3d2 hybridization, which is outer orbital complex, high spin complex. This is paramagnetic nature. With 4 unpaired electrons. This is in paramagnetic nature with 4 unpaired electrons. Hence, all the complexes successfully explained by valence bond theory, but that quantitative approach is not given. That quantitative approach also given by crystal field theory. Okay, in this way, that 6 complexes which were explained in valence bond theory, now I took example and I explained. Are you clear, man? Observe this final example also. I hope you are clear about this. And next drawback of valence bond theory is it could not explain colors of the complexes. It could not explain colors of the complexes. Now next side heading in CFT is colors of the complexes. Generally, all the complexes are colored. Okay, but main characteristic I will say, if they give any sort of complex, suppose they give one complex with Zn plus 2 and they give complex with CO plus 3, this is cobalt. CO plus 3 configuration, argon 3d6. This is in presence of weak field ligand. 1, 2, 3, 4, 5, 6 unpaired electrons are present. If the complex has unpaired electrons, definitely it is colored. If the complex has unpaired electrons, definitely it is colored. Let us consider Zn plus 2. Zn plus 2 configuration is argon 3d10. Zn plus 2, what is the configuration? Argon 3d10. 3d10 means one, 2, 3, 4, 5, 6, 7, 8, 9, 10. All the electrons are paired, no unpaired electrons. If there are no unpaired electrons, this is colorless. Now, why we have to see that why these are colored in nature. If a complex has, if a central metal atom or ion has unpaired electron, then why it is colored? Now we have to see the point. Okay, is it clear now? If it has no unpaired electron, no problem at all, that is colorless. But if it has unpaired electron, it is colored. Now why that unpaired electron is reasonable for color? See, let us consider one example, Mn plus 3. Mn plus 3 in presence of weak field or strong field. Anything, no problem. Let us consider weak field. Okay, strong field again. Then Mn plus 3 configuration, argon 3d4. In presence of strong field, this 3d4 can be written as 1, 2, 3, 4. Correct? 3d4. Now, see, our 3 are in presence of strong field ligand or weak field, splitting is happened. So, 3 orbitals are in ground state, 2 orbitals are in higher energy state, low energy state, higher energy state. Here we have 4 electrons, 1, 2, 3, 4. Okay, this is the complex. This complex is exhibited to, I am going to rub this one now. This is Mn plus 3 complex now. This complex is exhibited to sunlight. Sunlight contains all the 7 colors. Sunlight contains all the 7 colors with GR. Okay, now total BGR sunlight is going to be fallen on the complex. At that time, what is going to be happen? Out of these 7 colors, any one color which is responsible for the transition of this electron to higher energy, this is separated by some energy difference, correct or not? That means some wavelength. The wavelength which is matched with this, see, violet has some wavelength, indigo has some wavelength, like that every color has some suitable wavelength. the wavelength of the particular color and this energy state, if it is suited exactly, then out of these 7 colors, let us consider that red color wavelength is suited with this energy transition. Then what will be happen? Out of VIBGR, red color is absorbed by this electron. Out of VIBGR, red color is absorbed by the electron. Then this electron is excited to high energy state. Out of VIBGR, red color is absorbed by the electron. This electron is excited to high energy state. Then remaining all colors are there. No? All colors will not come out. Okay, exactly for this red, some complementary color will be there, like green, or otherwise after removal of red, remaining colors are dominated with some complementary color of red. Then green color, let us observe green color. So at once red is observed here, this complex is giving out green color. Suppose this complex is giving out green color. Here observer is present here. The green color is fallen on the observer eyes. Then this complex is colored as green color complex. This type of transition was not explained by valence bond theory because they did not consider splitting. Splitting in same d orbitals was not considered by valence bond theory. Okay, but this was considered by crystal field theory. The color which is coming out after the absorption of this red color with electron, that color is called complementary color. Once again, total VIBGR is going to be falling on this electron. This electron is excited to high energy level. Then remaining amount of color is there. Na? It is dominated with green color. That green color is coming out. Means wavelength correspondence. Red color, emission of light, it is suited with green color. According to that, green color disappeared. Suppose some yellow color is observed. Yellow color complementary color is orange. Then that complex is observed as orange color. Please remember, what is the complementary color it is coming out? That is appeared to the observer eyes. Here green color is the complementary color. Red is absorbed and that electron is excited to high energy state. Okay, in this way, colors of the complexes was explained successfully by crystal field theory. I will give little bit more clarity about this complementary color in next class. Okay, ma'am? I hope you are clear. Just observe this diagram, all of you. Okay, ma'am. So everyone, are you clear? I think in today's class. In today's class, we have seen some points in CFT and in magnetic properties of valence bond theory. What are the examples we took? Why those electrons are getting paired in some particular complexes, only that reason we have seen. And what about the colors of the complexes we have seen? Okay, these colors of the complexes in next class I will continue. I will give little bit more clarity about this complementary color. Okay, thank you. That is about today's class. Thank you all.